Yes, I would like to join the others and thanking the organizers for invitation. I must say that I adjusted my talk a little bit based on the kind of discussions which we had earlier today. But since I'm now in a metrology session, maybe I'll start by noting that quantum computer in reality is just like a highly entangled atomic clock. And of course, this kind of precision of atomic clock is really staggering. So what's different for a quantum computer is to really enable quantum computation, we cannot just let our atoms, our qubits, to idle. We need to constantly entangle and disentangle them. And actually, as already was kind of indicated earlier today, the key challenge in building a scalable, useful quantum computer is associated with errors. So in particular, most kind of known useful algorithms may require many billions of operations, and it's just not really conceivable to kind of perfect quantum logic, for example, entangling operations at this level. So basically, this issue has been recognized early on, and for this reason, many people believe that actually, quantum computing will never be, practical, will never be realized. But then there has been a development which have been already mentioned, quite ingenious, and this development is quantum error correction. So kind of the idea comes from classical error correction, is to basically, introduce some redundancy. So classically, for example, you can encode 0 in 3 zeros and, just use majority voting. So this idea, at least kind of on the surface does not extend well to quantum computing, because there are things like no cloning theorem. You cannot duplicate quantum information. You also, usually when you measure, you collapse the state. But nevertheless, it turns out that you can actually generalize this classical error correction ideas, by essentially in taking a qubit and encoding it non-locally among several physical qubits to create the so-called logical qubit. And this basically, you essentially use entanglement to store the information, and you use so-called stabilizer measurements, basically, measuring, the checks whether if the error, is occurred, to actually preserve quantum information during the quantum computing. And kind of at a high level, the idea is by being delocalized, this logical degree of freedom, this encoded degree of freedom, is hard to manipulate accidentally. And this was kind of an ingenious kind of ideas late in the 1990s that, people like Peter Shor and Andrew Steen and also Alexei Kitaev, John Preskill, and many others have developed. But you already see here that, these kind of techniques can be challenging to implement in practice. For once, you need to have many physical qubits to encode a single logical qubit. And secondly, for that same reason, the information is protected, that it's hard to accidentally manipulate. It's actually hard to manipulate it intentionally. So controlling these logical qubits is also very hard. And so in preparation of this talk, I actually recalled this kind of the article, which actually was much discussed in the late 1990s, was really kind of written by the people who were really at the time leading experts in kind of experimental quantum entanglement. And so basically the argument was quite simple. It's kind of, appealing to kind of even kind of on all the experts, So essentially building quantum computer is like, creating Schrödinger cats, and the quantum error correction is essentially encoding these cats into different cats, and that seems hard. And in fact, they, part of this, they talked about error correction. They said, therefore, we think it's fair to say that unless some unforeseen new physics is discovered, the implementation of error correcting codes will become exceedingly difficult as soon as one has to deal with more than a few cases. So, to some extent, they were correct. So it actually turned out to be quite challenging. It took more than 2 decades to start really kind of even testing this idea. And again, the key challenge is logical qubits are very hard to build and control. And in fact, only very recently, some truly pioneering experiments in the field have implemented small number, like 1 or 2 logical qubits and maybe 1 gate operations. But it's actually kind of ironic. In fact, some of the techniques which I used to implement this were pioneered by Serge and Jean-Michel, and you'll see this actually coming again. So basically, what I would like to discuss now is kind of progress towards realization of these techniques. And our experimental platform will make use of atoms trapped in optical tweezers. So this is kind of a complementary technique to manipulate cold neutral atoms complementary to optical lattices, where we basically start with atoms individually trapped in optical tweezers and loaded kind of randomly. And then, we basically extract the entropy by just figuring out which traps are full and which are empty, and then just rearranging atoms in a desired configuration. So after this procedure, these atoms are sitting a couple of micrometers from each other, and to actually make them interact, we excite them into Rydberg states, again, following pioneering ideas of Rydberg spectroscopy done by Dan Kleppner, Randy is still as a student, and also Serge and his group and others. So this work is actually a joint project between my group and in collaboration with my colleague at Harvard, Marcus Greiner, and a colleague at MIT, Vladan Vuletic. So the kind of idea that we use to entangle atoms is something which we call Rydberg blockade. And kind of the idea is very simple. So, we make use of the fact that the Rydberg atoms have long lifetimes and very strong interactions. And if we try to excite these atoms resonantly, and if the atoms are very far away, they just, don't interact, they undergo independent excitation, independent Rabi oscillation. But if they come close together, then this interaction grows very rapidly, like 1/6. And actually, once the atoms are closer in a certain distance, these interactions between atoms become so large that it basically prevents one to excite more than one atom. So, and this is an essence of this Rydberg blockade. This is actually a very good mechanism to entangle atom because it's very robust with respect to motion, position. So it actively makes the interaction digital. So it's actually a very important feature which you will see will play a role. So all in all, the way how this approach will work, we will assemble some arrays of atoms, we'll subject them to some kind of pulses, and then we'll make a measurement. And this actually in the last 5 years, this has been really exploding field, with kind of many research group exploring different directions. A couple of 100 experiments are being constructed now, and actually at least 6 startup companies are trying to commercialize this technology. So in our lab, we actually already are working with the 3rd generation of this atom array system, and it actually has 2 elements. So one element is a special light modulator, which can create a large number of static trap in arbitrary configuration. And another one is a second channel. The device we actually now often rely on involves 2 acousto-optic deflectors. So it's a kind of acoustoptic deflector is basically, something which takes a laser beam and just, deflects it using, sound waves. And by using 2 of them, what we can do, we can actually very rapidly move these traps around and kind of change the atom. So this 3rd generation has a couple of upgrades. It has larger systems, high fidelity, and more advanced control. So basically, this shows you a scale. So we can actually now trap, over 1,000 atoms and kind of reliably, for example, sort, something around 500 or so atoms. And so this kind of using the systems actually has been a lot of fun in very different directions, analog simulations, dynamics, probing topological physics. So actually, there is a system of this type now available online. It's from our startup company, Query Computing. But today, I will actually want to really focus on digital processor and exploring this error correction frontier. So the key kind of idea here is to use what we call a reconfigurable architecture. Usually, when you build, for example, a superconducting processor, you basically design it, you design a connectivity and fabricate it, and it's fixed. So here, if we encode qubits wisely, for example, encoding them into these hyperfine transitions of the basically of the atom, which is actually our clock states. So we first off make these qubits live for a very long time, but then also we can actually move atoms around in tweezers while preserving coherence. And so this gives rise to this reconfigurable architecture where we start with some atoms, where certain pairs of atoms are close to each other. We can excite them to Rydberg state with short pulses, entangle them, then stop this excitation, move the atoms around, entangle them again, and that's the idea. So basically our architecture becomes kind of a living organism. And so basically this architecture gives rise to unique opportunities, both enabling non-local connectivity and parallel, very efficient classical control, which you'll see is very important. So here is one example. It's in implementing some paradigmatic error correction code called toric code, where basically you encode information into grids of physical qubit called the so-called data qubits, which are positioned like this on a torus. And then you have another set of qubits called ancilla qubits, where you actually use them to measure the stabilizers, to detect where error has occurred. And actually you would say, well, making this figure on the torus is actually hard, but we can actually use it by using this moving atom architecture. So here what is shown is that some ancilla atoms are moved around, and basically the red square is a quantum gate. And then what you see here is that first we basically do some local checks. We move, atoms around and then move all the way to the right and then move ancilla to this readout. So the beauty of that is that the circuit is programmed by just specifying very few numbers, for example, the special light modulator to keep stationary qubits and acoustoptic deflector to actually define a waveform. And most importantly, so here we actually encode two logical qubits, they encode it, going around this torus one way and the other. And it's actually done by using just two control parameters, which are basically voltages, which move the atoms, up and down, left and right. So to kind of, use this approach to do serious error correction experiment, we had to do technical upgrades. I'm not going to talk about them in details, but we now have, fairly high fidelities for 2-qubit gates. We also have arbitrary programmable parallel single qubit gates, also with quite high fidelity. And we also can now measure atoms mid-circuit, during the kind of computation process, but simply taking some atoms and moving them in a separate zone where we can image them and actually then basically preserve the atoms which are not in this image zone and kind of image atoms in this image zone with very high fidelity. And so altogether, this actually combined allows us to really realize what we call a first generation logical processor, where we have actually storage zone, we have entangling zone, and we have redown zone, and you will show now how this approach works. So the key component of that is efficient logical qubit control. And to understand its importance, let's just consider kind of a simple element of this logical operation, just two logical qubits which are encoded, for example, in something like surface code, something which already was mentioned. So usually to make the gate between them, so you have to somehow move information from one logical qubit over another, doing some kind of braiding or swapping if you want. And that's actually very challenging. In fact, to make it fault tolerant, you have to constantly measure these, ancillas. You basically need to do what's called D rounds of error correction, where D is a linear dimension of the system called distance. But instead, what one can do, one can just, move them on the top of each other, and then do something which is called transversal synod. And so in this transversal synod, it turns out to be a very powerful approach, because basically it's inherently fault tolerant. The errors don't spread. So it's long range. You can connect any qubits to any other qubits. And most importantly, we can do all of these operations by essentially treating each group of atoms as one single macroscopic atom. We can basically with one control, move and enable this kind of gate. So let me just quickly go with a couple of examples. This approach works extremely well. So one of them is to just do a logical entangling gate with surface codes. And so in this approach, you prepare these two surface codes in different states, by kind of, encoding and measuring different types of stabilizers. And then you just bring these two surface codes, on the top of each other, pulse a laser, put them away. So these are distance-free codes. We could also explore it with distance 5 or distance 7. So distance 7, even a single code has never been actually prepared up to now. And in this case, after we do this operation, we clearly see that the distance surface codes are entangled. And moreover, if you look at the quality of entanglement, it clearly is improving with the code distance, and this is a hallmark of the quantum error correction. By making the system larger, your error is suppressed. There are various caveats about these results. So we have to use some what's called correlated decoding. Actually, this is something, one could guess, but we kind of discovered it. This is also just one round of error correction. But nevertheless, it already shows that we can really, do these operations and explore, and this is really an exciting scientific frontier. The second example is a fault-tolerant preparation of the states. So in the previous example, our preparation was not fault-tolerant. So, but here we can use the ideas proposed by Andrew Steen, sometimes called Steen error correction, where you prepare two codes non-fault-tolerantly, and then just do a gate between them. It's kind of like a logical Ramsey experiment, if you want, and then measure the one qubit. And if this one qubit is in 0, you are guaranteed the second one should be in 0 with high probability. And in this case, we see that this preparation performs extremely well. So it actually will break even. The fidelity is better than physical fidelity, both in terms of spam, but also in terms of gate fidelity. Experiments like this have been done for 2 qubits, but in our case, we can do it in parallel. We can do it, for example, in 4 pairs simultaneously. And what you see that in this case, we now have, after the preparation, we actually have qubits in which we can do circuits. So, and in fact, we did some circuits with the GG states and did teleportation with this logical qubit. So I'm not kind of going to dwell on that, but just in my last minute, I will show you, hopefully, which actually really some kind of exciting new development, and which shows that we are now entering this era of what I would call early fault-tolerant quantum computation. So here, what we need to do, we need to think about what algorithms we want to implement, and we need to pick the code correctly, and then we need to basically make them comparable to this hardware capabilities. This is sometimes called approach called co-design. And the example I will give you will include something which is called non-Clifford operation. So it turns out that a circuit of the type that I showed before, it's actually Clifford circuit, is actually kind of relatively simple in the sense that it can create entangled state, but it can be simulated classically. So to do the circuit, which you cannot simulate classically, requires something which is sometimes called quantum magic. It's so-called non-Clifford operation. And usually these non-Clifford operations are very hard and very expensive. But, it turns out that we can actually, by utilizing a clever code, so in this case, we're using small three-dimensional code, 832 code, we can actually prepare, we can both prepare the kind of states and actually do non-Clifford operations. And this is done by basically, by tinkering, with qubits individually in each of these, three-dimensional code. And it turns out you can implement this TCZ operation, which is non-Clifford. So I'm running out of time, but the kind of circuit here we do is very similar to this sampling circuit, that John mentioned. But this in the circuit, we implement highly non-local connectivity. In fact, what we are doing, we are creating hypercubes. We are creating 4-dimensional hypercubes of logical qubits, and actually it corresponds to 7-dimensional hypercubes of physical qubits. So the way how you test the circuit, you can, for example, do a sampling experiment. And this actually really kind of beautifully shows how error-corrected quantum computing is different from non-error-corrected. So basically, in the sampling experiment, so here is a theory which we expect is a kind of a speckle pattern is basically bit string, probability. So if you don't just do any error correction, if you you see some kind of patterns. But if you now start introducing, if you start conditioning this result on certain stabilizers, being correct, so in this case, actually it's error detection, it turns out, not quite error correction, you see that this distribution really kind of emerges, and one can quantify it with things like XCB and stuff like this. So we have done these circuits with up to 48 logical qubits, and this is a logical circuit. It's actually over 200 logical gates, and what we see is that these circuits, outperform, for example, the best possible physical circuit which we can make by close to a factor of 100. And this really shows that these kind of early ideas of kind of error correction, really are starting to play a role. So I will actually finish with just, this is a movie how this circuit is made. So what you'll see here is that basically we are making in hierarchical structure larger and larger hypercubes, and then we would either run out of space and entangling zone, so we have to deposit one set of qubits and store it, and then make another, hypercubes with the other, and then eventually what we'll do, we'll actually bring these qubits together and entangle them into a logic. So, okay, this is actually only a start of the fun, but I will, try to finish here. So one could also, for example, do things like, scrambling measurement, measure entanglement entropy. Kind of it's related to the scrambling in the black holes, for example. But what you see here, it's actually a lot of fun, and it's a kind of, in a way, an experimentalist dream now. So it's a really exciting frontier involving building and using complex logical quantum processors, which is really becoming a reality. So of course there are many challenges in the field, and I look forward to to see how this development affects the discussion between Bill and Carl. But I think here I would like to finish by thanking the people whose blood and sweat resulted in this work, and thank you very much for your attention.